The ketogenic diet, characterized by high fat intake, moderate protein, and very low carbohydrates, has drawn increasing scientific attention not only for its metabolic effects but also for its potential neuroprotective properties. One of the emerging areas of interest is its influence on brain glycogen accumulation, a subject that until recently remained largely unexplored. While glycogen in the brain is far less abundant than in the liver or muscles, it plays a crucial role in supporting neuronal activity, especially under metabolic stress. However, in certain neurodegenerative conditions and metabolic disorders, abnormal glycogen buildup, including the formation of insoluble polyglucosan bodies, has been linked to cellular damage and impaired brain function. Against this backdrop, ketogenic diets present a unique metabolic environment that may reduce the likelihood of such pathological glycogen accumulation and support neuronal survival through alternative energy pathways. By drastically lowering carbohydrate intake, ketogenic diets reduce circulating glucose and shift the body's energy metabolism toward the production of ketone bodies, primarily beta-hydroxybutyrate and acetoacetate, from fatty acids. These ketones become the brain's primary fuel in the absence of sufficient glucose. Interestingly, neurons and glial cells adapt well to using ketones, especially during fasting, infancy, or carbohydrate deprivation. This shift in fuel usage may reduce the brain's dependence on glycogen as an emergency energy buffer, particularly during heightened activity or stress. With reduced glucose flux into the brain and less glycolytic activity, the demand for glycogen storage within astrocytes may diminish, potentially preventing the aberrant accumulation of poorly structured glycogen-like substances seen in diseases such as Lafora disease and adult polyglucosan body disease. The ketogenic state also appears to modulate key enzymes involved in glycogen metabolism. For example, low glucose availability naturally downregulates glycogen synthase activity, the enzyme responsible for building glycogen chains. Meanwhile, increased fatty acid oxidation and ketone availability may shift energy homeostasis in a way that indirectly favors glycogen conservation in non-pathological amounts while preventing the buildup of dysfunctional or non-metabolizable glycogen aggregates. This regulation is particularly relevant because abnormal glycogen structures are not merely inert storage mistakes. They can physically disrupt cellular architecture, interfere with synaptic function, and provoke immune responses when misidentified as foreign material. By minimizing the conditions under which these malformed glycogen granules are formed, ketogenic diets may offer a form of metabolic hygiene for the brain. Additionally, the use of ketones as fuel in the brain has been shown to enhance mitochondrial efficiency and reduce the generation of reactive oxygen species. This is a critical point, as oxidative stress and mitochondrial dysfunction are central drivers of neurodegeneration. Since abnormal glycogen metabolism often correlates with oxidative stress and impaired mitochondrial function, shifting away from glucose-heavy metabolism may break a vicious cycle in which poor glucose handling leads to glycogen mismanagement, which in turn exacerbates oxidative damage. In animal models of epilepsy, Alzheimer's disease, and traumatic brain injury, ketogenic diets have been shown to improve cognitive outcomes, reduce neuroinflammation, and preserve synaptic integrity, effects that may be partially attributed to both ketone metabolism and improved intracellular energy regulation. It is also worth noting that the ketogenic diet influences not just neurons but also astrocytes, the primary sites of glycogen storage in the brain. Astrocytic function is intimately tied to the support of neuronal activity, including buffering extracellular potassium, recycling neurotransmitters, and managing energy delivery through the astrocyte neuron lactate shuttle. Under ketogenic conditions, astrocytes shift their metabolic profile as well, potentially reducing reliance on glycogen breakdown to fuel neuronal demands. This change might lower the burden on the glycogen turnover system and reduce the risk of storage anomalies, while still preserving the cell's ability to meet acute energy needs via ketone-fueled ADP generation. However, this metabolic shift is not without caveats. Glycogen, while limited in amount, is important for maintaining proper brain function during acute challenges like hypoglycemia or ischemia. In such scenarios, the immediate availability of glucose-derived energy can be life-saving. Therefore, long-term suppression of brain glycogen stores through strict ketosis might reduce the brain's resilience to short-term glucose shortages, especially in individuals with compromised metabolic flexibility. Moreover, while ketogenic diets may be protective in certain contexts, they are not universally beneficial. They can lead to nutrient imbalances, dehydration, and lipid abnormalities if not properly managed, and their suitability varies across age groups, health conditions, and genetic backgrounds. Despite these limitations, the evidence continues to support the idea that ketogenic diets offer a compelling metabolic strategy for preventing or mitigating certain forms of glycogen-related brain pathology. Whether by reducing the synthesis of abnormal glycogen, enhancing mitochondrial function, or simply offering a cleaner-burning alternative fuel, ketosis appears to introduce a new layer of control over brain energy metabolism. It is a promising direction for therapeutic exploration, particularly in conditions where conventional glucose-centric energy strategies fail or even exacerbate the underlying disorder. As with all interventions in complex systems like the brain, the goal is not necessarily to eliminate glycogen, but to ensure its regulation remains balanced and functional. Ketogenic diets may help achieve this by imposing a systemic energy environment that discourages the erratic or excessive formation of glycogen while bolstering the brain's capacity to function under alternative energy sources. In this light, ketosis is not just a metabolic curiosity. It may be a key to unlocking greater control over neurodegeneration, energy dysregulation, and the subtle biochemistry of cognitive resilience.